So this is for the Neumann boundary condition. So you're evaluating everything here at x is equal to x3. So when you plug x3 into n1, n2, you get 0 for n1 and 1 for n2.
Okay, so basically we have to.
Yeah, so remember this is for element 2. So element 2, the shape functions look like. Well, that's the shape function derivatives. So the shape functions look like this. So x minus 20 and 5 minus 6.
So of x we put 20.
Exactly. Yeah.
Thank you. Or the range of the elements, so you just give it. If it's not given in the question, then we take everything equal, right?
Exactly. Yeah. Good. How are you?
Yes. Is there 2D stuff on the midterm?
No, there's not. Yeah, I'm gonna make an announcement today. I know I left it on that study guide, but there's no 2D stuff. Yeah. Yes. All right, it's 5:30. Let's go and get started. All right, good afternoon, everybody. How's everyone doing today? Good, good, good. All right, so we're in the final stretch of the semester. So we have just 6 more lectures to go. And one of them is the exams. We just really have kind of 5 more lectures to go. So with that said, everything that we're covering up to this point, from this point forward is going to be pretty important for the project. So not too many lectures, but they're all going to be pretty impactful. So, yeah, we're definitely take this course down to the council wide. Okay, so some announcements before I begin today. So first thing, remember our midterm exam is this Thursday. It's going to be in class, and so please make sure you are here for that. I know a couple people asked me over the weekend because I think on the study guide I had included some 2D finite element stuff. There's going to be no 2D stuff on the exam. I forgot to take it off the study guide, so the exam is just going to be just based on 1D stuff. So basically, just exactly like the last homework assignment. In fact, you can expect the problem to be very similar to the last homework assignment. Okay. Yeah, so I forgot to take it off, but 2D stuff is mostly just for the project, and so yeah, just make sure you're prepared for that. Okay. All right. Any questions before I get started for today?
How many questions are going to be on the exam?
There's going to be 4 conceptual questions and 3 problem-solving questions. Yeah. I just burst into here. That's pretty cool.
I was listening to the lecture on my.
Oh, I see. All right, let's get started. Okay, so where we were last Thursday, we were going over 2D finite elements. In particular, we're looking at 2D heat conduction. Okay. So in other words, we're solving heat transfer problems or heat conduction problems using finite elements, right? And again, the reason we're doing this and the reason we're kind of making this shift from structural mechanics to heat transfer is that once you get into multiple dimensions, the heat transfer equation becomes a lot easier to solve than the structural mechanics one, just because temperature is a scalar field versus deformation, which is the vector. Okay. In particular, we were looking at the triangular element. Or I should say the 3-node triangle. Okay. And so 3-node triangle, just like its name implies, it has 3 nodes. Okay. And one trend that you'll see, especially as you dive kind of further and further into finite elements. So let's say that you take more advanced classes after this, is that the number of shape functions in an element matches the number of nodes, right? So if you have 3 nodes, we have 3 shape functions. Okay. So that's going to be N1 of X and Y, N2 of X and Y, and N3 of X and Y. Okay. So last time we discussed or we kind of showed what the forms for these shape functions are. I'm not going to write them again, just because they are a little bit lengthy. But just know that the form for all 3 shape functions are the same. So this is a linear element, right? And so that means our shape functions here are also going to be linear. So the shape functions Ni of X and Y are of the form A0 plus A1X plus A2Y. Okay. So 3 unknown coefficients and 3 terms. So we have a constant term, a term that's linear in X, and a term that's linear in Y. Okay. All right. So I'm bringing this up again just to kind of remind you that when you take a derivative of a linear function like this, the derivative is nothing more than just a constant. Okay. And so we're in 2 dimensions here. So of course that means we can take derivatives in 2 directions. We take a derivative in X, we take a derivative in Y. Doesn't matter which direction that we take it in, we're always going to end up with a constant. Okay. Okay. And so exactly where we left off is that we came up with an expression for the element stiffness matrix. And so through through our kind of integration by parts in 2 dimensions, we were able to come up with the following form, right? So this equation that I'm going to write down right now is valid for every, no matter what element type that you're looking at, even 3D elements. It's just that exactly how you implement each of the terms is different based on the element shape. Okay. So the element stiffness matrix is given by double integral of the gradient of the weighting function, W, okay, multiplied by K. K here is our thermal conductivity. Okay. In most cases, your thermal conductivity is just going to be a constant. And then we're going to multiply this by the gradient of our temperature field, T. Okay. And we're going to integrate that over D. All right. So that's what our element stiffness matrix looks like. Now, when you apply this equation to different element types, what that involves basically is plugging in different expressions for these two right here. Okay. Okay. So depending on the element type, the exact shape, the form, how many shape functions we have, we're gonna have different expressions for these two gradients here. Okay. And the way it works, and so we're only gonna really apply this to 2 different types of elements. So we're doing it obviously now for the triangle, and then we'll do it for the 4-node quadrilateral as well. But they all kind of follow the same trend. So, whenever you have gradients like this in your weak form, the way you turn it into a finite element form is that you put the circle terms in terms of the shape functions of the element. Okay. All right. So I'll give you an example in terms of or I'll show you what these look like for the triangle. And so for a triangle, we have 3 nodes and we're in 2 dimensions, right? And so our gradient of W here is equal to row vector W1, W2, W3 multiplied by this 3x2 matrix. So you have partial N1, partial X, partial N2, partial X, partial N3, partial X, partial N1, partial Y, partial N2, partial Y, partial N3, partial Y. Okay. And then we have a mirrored expression for the gradient of temperature. All right, so typically for the weighting function and the temperature, we typically transpose them just to make it a little bit more convenient for developing matrices. Okay. So this one has very similar elements. They're just kind of flipped. You have partial N1, partial X, partial N2, partial X, partial N3, partial X. Okay. This time they're all in the same row as opposed to all in the same column. And partial N1, partial Y, partial N2, partial Y, partial N3, partial Y. Okay. And they're multiplying this by the column vector T1, T2, T3. Okay. So these are the expressions for the 3-node triangle, right? And so notice that, because our triangle has 3 nodes, has 3 shape functions, and so that's going to affect the size of this, okay? And the number of, and the other dimension depends on the dimensionality of the problem. So since we're in 2D, we have 2 columns for the gradient of the weighting function and 2 rows for the gradient of the temperature. All right. And so when you multiply these two things together, right? So you're going to take these expressions for the gradient, plug them directly into our integral expression up here. You're going to get a matrix multiplication. So you're going to multiply the matrices. And then what you're going to get is you're going to get a 3 by 3 matrix in the end. Okay. So I'm not going to write out the full expression for the element stiffness matrix again. That's the last thing that we wrote last time. And if you look at it, you'll understand why. It's very big and involves a lot of derivatives. So, yeah. Question, Timid? Okay. Any questions on this so far? Okay. All right. So before we do an example, I do want to give you the expressions for the forcing vector. Okay. So we're not going to do any calculations on this right now, just because it is a little bit complicated to do without Gauss quadrature. But I at least want to show you kind of what it looks like. Okay, so for the element forcing vector, we're going to use the same shape functions, right? So that's kind of the theme of this whole, this whole unit here is to use the shape functions. Okay. And we're going to plug them into the integral term with the body force, or excuse me, the integral term with the thermal generation, as well as the line integral containing the Neumann boundary condition. Okay. So let me go ahead and write out each of these individually, right? So if you look back at our weak form, right, the weak form for the 2D heat conduction problem, we had let's start with the thermal generation term. So our thermal generation term was a positive double integral of W of X and Y multiplied by thermal generation function X and Y dA. Okay. Remember this S of X and Y here, this is our thermal generation function. And so what we're going to do from here, we're going to plug in for the weighting function W, right? Because we have an expression for the weighting function W is in terms of our shape functions. Okay. So that's what we're going to do in that step. So we're going to plug in for our shape functions there. Okay. And so we end up with W1, W2, W3. Okay. Remember, those are just coefficients, and so we don't integrate them, or we can factor them out. Okay. Multiplied by double integral of N1 of X and Y, N2 X and Y, and 3 X and Y. Okay. Multiplied by the thermal generation function S of X and Y dA. Okay. Notice how we don't have any derivatives here because we're not plugging in the gradient of W, we're just plugging in just W by itself. Okay. So W by itself just involves just the regular shape functions there. Okay. All right, and then we also have our Neumann boundary condition term. So our Neumann boundary condition term was this line integral. Okay. Remember what that symbol means. So that integral with the circle through it, it looks like a musical note, but it's not. It's a line integral around the boundary of our element. Okay. Times W Q bar ds. Okay. And then once again, we're just going to simply plug in for our W here. And so if we do that, we get minus W1, W2, W3, a line integral around the boundary of N1, N2, N3. Okay. That N1, N2, N3 are still functions of X and Y times Q bar ds. So actually, let me be a little bit more specific. So this line integral here, this integral is specifically around the boundary of our point. And since we have a 2D element here, our boundary around it is going to be an edge, so a line. Okay. And I'll leave a little footnote here as well that, and this, and honestly, we're not going to really evaluate this term here until the project. And so you'll kind of see what I mean once we get to that part of the project. But this term here is only going to be active whenever we're on a Neumann boundary. Okay? So we're going to only evaluate this if Neumann boundary condition is present. So that means on some elements, we're not going to evaluate this at all if it's not on the boundary of a Neumann boundary. And even for the elements that are bordering a Neumann boundary condition, usually only one or two edges of that element are actually bordering it. So we're only going to evaluate this on those. Okay. But we'll cross that bridge when we get there. So we're not going to actually deal with this until not even part 1 or part 2, until part 3 of the project. All right, any questions on this before we jump into an example? Okay, all right, so let's do an example. Okay, so let's consider the following triangles. Okay, so we're gonna have 2. All right, so basically, so what we have here is actually we have a quadrilateral that we've kind of split into 2 triangles, right? So any kind of square or rectangle, if you draw a line across the diagonal, you get 2 triangles. Okay. All right, and so we have coordinates for all of these nodes. And so the coordinate bottom left will say 0, 0. This one will be 1, 2. This one will be 2, 1. And the one up here will be 3, 3. Okay. All right, and so what we're interested in, we'll call this element, we'll call it element A. And the second element we'll call element B. Okay. So let's compute the element stiffness matrix for each of these elements. All right. So if you want to do this kind of seriously, the best way to do it will probably be to use a calculator or MATLAB, just because it involves a lot of kind of tedious math. But we'll do our best right now to kind of set up the problem, just so you can kind of visualize what the calculations are doing. Okay. Okay. So actually, first, let me go ahead. So I'm just going to tap back here and show you the end of the notes from last time. You don't have to write anything down, because you've already written this down. Okay. So if we look back at the notes from last week, we can see that the element stiffness matrix is given by this expression right here, okay? Where basically you have all the shape function derivatives, okay? And the shape function derivatives were given by these expressions right here. Okay, so we have a difference in the y coordinates, difference in the x coordinates divided by 2 times a. Okay, so basically, what the first thing we're gonna do is we're gonna evaluate all these shape function derivatives for the problem at hand. Okay, we're gonna compute its area and then just kind of plug everything in. Okay, so let's start with that. Okay. All right, so actually let's start with element A too. Let me start with that. Okay. So element A is this element right here. Okay. And just because it'll be useful for us in the calculation, let's go ahead and label these nodes as well. So let's label the bottom left node, we'll call it node 1. The top node here, we'll call it node 2. And then the bottom right node, we'll call it node 3. Okay. Just because it'll be convenient for us when we're taking differences of these coordinates. All right. So let's start with partial n1 partial x. Okay. So if you look back at the expressions from the previous page, partial n1 partial x is y2 minus y3 divided by 2a. Okay. All right, so if we plug in for this, the area, or I guess the difference in y2 and minus y3, right? So y2, the y coordinate of node 2 here is 2. The y coordinate for node 3 is 1. Okay. And we're going to divide this by 2 times a. Right? And so if we do that, we get 2 minus 1 on top is 1. We get 1 over 2a. Okay. I'll compute the area in a second. Or you'll see from the problem that the area doesn't matter all too much. It's going to cancel out. All right, so next let's do partial n2 partial x. Okay, so partial n2 partial x is going to be y3 minus y1 divided by 2a. All right, so let's go ahead and subtract these. So y3 here is 1 minus y1. The y coordinate for node 1 is 0, so we have 1 minus 0 divided by 2a. And this is equal to, once again, 1 over 2a. Okay. Next, we have partial n3 partial x. Okay. Partial n3 partial x is y1 minus y2, all divided by 2a. Okay. So we plug in from the problem here. The y coordinate for node 1 here is 0. The y coordinate for node 2 is 2. So we have 0 minus 2, all divided by 2a. Okay. And so what that equals to is minus 2 over 2a, or in other words, minus 1 over a. All right, so let's do the same thing for the y derivatives as well. So we have partial n1, partial y. This expression is x3 minus x2, all divided by 2a. So we come back up to the diagram here. The x coordinate for node 3 is 2. The x coordinate for node 2 is 1. So once again, we have 2 minus 1 over 2a. This is 1 over 2a. Okay. we have partial n2, partial y is equal to x1 minus x3, all divided by 2a. Okay. So the x coordinate for node 1 is 0. The x coordinate for node 3 is 2. Okay. So we have 0 minus 2 divided by 2a. So this is equal to a minus 1 over a. Yes.
Why is it 1 minus 3 for y, but 3 minus 1 for x?
Yeah, it's because of the exact forms of the shape function. So and so granted we did skip these derivations, but if you look back from the previous notes, n1 looks like this, right? And so when you take the derivative of that with respect to x, we get y2 minus y3. But then when you take the derivative of that with respect to y, it's x3 minus x2. And that's mostly just because of this requirement here. And the reason we kind of got those coefficients was to basically enforce the fact that, you know, the solutions at each of the nodes have to equal, you know, the nodal solutions, T1, T2, T3. Yeah. So it's just in the shape functions themselves, they just ended up swapping. Okay. And then finally, a partial n3 partial y. And so that is x2 minus x1 divided by 2a. So the x coordinate for node 2 is 1. And the x coordinate for node 1 is 0. So we have 1 minus 0 divided by 2a. And that's equal to 1 over 2a. Okay. All right. So now the fun part, or not the fun part, right? So now that we have the shape function derivatives, we can go ahead and plug that into our expression for the element stiffness matrix. So, you know, of course, we're not going to do that right now just because it's a little bit too time consuming to do. So normally, you know, you would use a computer for this. Okay. So I'll skip all that. It's a lot of 1/3, you know, 1/2 plus ones and things like that. Okay. And so what we get from this is integral, double integral of k multiplied by this 3 by 3 matrix. Okay. And so our 3 by 3 matrix in this case is 2 over 9, 0, minus 1 over 9, 0, 8 over 9, minus 6 over 9, minus 1 over 9, minus 6 over 9, and 5 over, okay, 8. Oh, I forgot to compute the area. So the area, so you're probably wondering where the 9s came from. The 9s came from the fact that the area for the triangle, I think normally people are accustomed to computing the area of a right triangle. But if you know the coordinates for all the nodes of your triangle, you can actually compute the area from it. Okay. So this right here is area of a triangle. Based on nodal coordinates. So the area of a triangle based on nodal coordinates is 1/2 multiplied by x1 times y2 minus y3 plus x2 y3 minus y1 plus x3 y1 minus y2. And of course, we have all this information. We can plug it in from the problem. And so we plug all this in, we get an area of 1.5. Okay. There's no units here, so the area is just 1.5. So that 1.5 you can plug into all these things here. So you can see that, we're going to get a lot of 1/3 and a lot of -2/3 and things like that, right? And when you multiply those things together, you get 1/9. All right. And so if we make life simple for us, right? And so, this by itself isn't the element stiffness matrix yet, because we also have to multiply by the K, right? And we also have to multiply by this integral over dA. Okay. So for this problem, just to make our lives a little bit easier, let's assume that K is equal to 6. Okay. And so if we assume K is equal to 6, and we notice that everything in this expression is a constant, right? And so if we assume everything is a constant here, everything can factor out of the integral itself. Okay. So that includes the K and this 3 by 3 matrix. Okay. And what we have is double integral of dA. And double integral of dA is just the area. Okay. The area of our triangle. Right. And we just computed the area of the triangle, which is 1.5. Right. And so this whole matrix is going to be multiplied by 6 times 1.5, which is 9. Okay. So let's multiply this entire matrix by 9, and then we're going to get our expression here. All right. So if we multiply the entire matrix by 9, we multiply the entire matrix by K is equal to 9, we get the following. So we still have our 3 by 3 matrix here, and then every entry we're just going to multiply by 9, which conveniently is just going to get rid of our denominator in this case. 2, 0, -1, 0, 8, -6, -1, -6, and 5. Okay. So that right there is the element stiffness matrix of our triangle. Notice how it's symmetric, right? And so just like all of our element stiffness matrices that we've seen in this class, it's a proper symmetric matrix. And so if you get an element stiffness matrix that's symmetric, then you're probably on the right track. Okay. All right. Any questions on this example here? Okay. All right. So that's the basics of this method here, right? And so all the magic that happens, in these types of problems happens in the shape functions, right? So if you kind of understand what the shape functions are and what their purpose is and how to use them, you're going to be in really good shape for this section of the class, right? Whether it be 1D or 2D. Okay, so let's move on. So let's move on to another element type. So let's move on to the 4-node rectangular element. And so we're going to see how things are a bit different for the 4-node rectangle. So the 4-node rectangle, just like its name implies, looks like a rectangle. And the number of nodes that it has is 4, right? So 1 for each corner. All right, so we'll call this node 1, node 2, node 3, and node 4. Okay. So it's x1, y1, x2, y2, x3, y3, and x4, y4. Okay. So the nodal coordinates for each of the nodes are known, right? Now I know the way that I drew here, it looks like a square, and so it seems like x2 and x3 are the same. But this is just arbitrary, so this can be for any for any coordinates. Okay. All right. And so just like we did with the linear triangular element, we're going to start with the form of the shape functions. Okay. And so our shape function forms, right? Keep in mind that we want to keep the function linear, right? Because linear functions have a lot of usefulness to us. It's pretty straightforward. And so we're given a0 plus a1x plus a2y. So that's the same functional form as our 3-node triangle, at least for now. But since we have 4 nodes in this element here, we actually need to add a fourth term. And so that fourth term is going to be a3 xy. Okay, so we add this fourth term because we have that fourth. And so if you look at that last term there, you'll see that it's not perfectly linear, right? So a1x, a2y, those are perfectly linear terms, just that they only have just one functional dependence, right? Technically, this is a product of two variables here, so x and y. But if you look at them individually, like individually in x and individually in y, that term is still linear. So we call this kind of the pseudo-linear term. So just a little bit of trivia behind that term, right? But actually, that term there is going to cause us a lot of issues that you'll see in a bit. Okay. All right. So just like before, right? The way that we're going to derive our 4 shape functions in this case is to require that our solution here matches the nodal solutions. Okay. And since we have 4 nodes here, that means we're going to have 4 equations that we need to solve for. Okay. So that means we're going to have t of x1 and y1 is equal to a0 plus a1 x1 plus a2 y1 plus a3 x1 y1. Okay. This has to equal the nodal solution at node 1, so this is equal to t1. Okay. We have t of x2 y2 is equal to a0 plus a1 x2 plus a2 y2 plus a3 x2 y2. Okay. That whole function there has to be equal to the nodal solution at node 2, so t2. Okay. Then we have t of x3 y3 is equal to a0 plus a1 x3 plus a2 y3 plus a3 x3 y3 is equal to t3. Okay. We have t of x4 y4 is equal to a0 plus a1 x4 plus a2 y4 plus a3 x4 y4. And that has to be equal to the nodal solution at node 4, t4. Okay. All right. So we have a really nasty system of equations, right? And so it's all symbolic, right? So we don't have any numbers to plug in. But it is a 4x4 system. So you have 4 equations, 4 unknowns. Your unknowns in this case, of course, are the A coefficients. Okay. So we have four unknowns in the equation, so we needed four equations to solve them. Okay. All right. And so after solving for those coefficients, after solving for those coefficients, what we do next is that we put the equation in the following form. And so we have t of x comma y is equal to t1 and 1 of x comma y plus t2 and 2 of x comma y, t3 and 3 of x comma y plus t4 and 4 x comma y. Okay. So basically we're going to group, we're going to get pretty complicated expressions for A0, A1, A2, A3, and they're going to involve all four of the t terms. But if we rearrange the equation algebraically to kind of group all the t1 terms together, all the t2 terms together, all the t3 terms together, all the t4 terms, right? We're going to get an expression which, whatever is multiplying by each of the t's, that's going to be our shape functions. Okay. iPad keeps doing that. Okay. So this will give us our shape function. And so if we do that, right? So of course, I'm skipping a lot of steps here just for the sake of brevity, but just know that there's a lot of kind of intense algebra that's going on in between these steps. Okay. All right, so our first shape function is going to be x minus x2 divided by x1 minus x2 multiplied by y minus y2 divided by y1 minus y2. Okay. And 2 is going to be x minus x1 divided by x2 minus x1 multiplied by y minus y1 divided by y2 minus y1. Okay. And then n3 is equal to x minus x4 divided by x3 minus x4 multiplied by y minus y4 divided by y3 minus y4. And then n4 is equal to x minus x3 divided by x4 minus x3 multiplied by y minus y3 divided by y4 minus y3. Okay. Right. So in this class, we're not going to do too much with the 4-node rectangle, at least not in this form, because we kind of have a big issue here, right? And so if you look back at our example for the 3-node triangle, right? It was a lot of math to do, right? And so even computing the shape function derivatives was a lot of math. But we kind of had a saving grace in the fact that all of our shape function derivatives in that case were constants, right? If we look at the shape functions here, and in fact, you don't even have to look at the shape functions. We know all the shape functions are of this form, right? So we know all the shape functions they have a constant term, they have an a1x term, an a2y term, and an a3xy term, right? So that cross term, that pseudo linear term is actually going to give us a lot of issues. Okay. Because when we form our shape function, remember when we form our element stiffness matrix, we're only taking first derivatives of our shape functions. Right? Okay. We're going to compute partial n1, partial x, partial n1, partial y, and the x and y derivatives for each of these, right? When we did this for the triangle, right? So when we did this for the triangle, we ended up with just constants, right? But if we do that for the rectangle, what we're going to see is that we're going to end up with non-constant expressions. Okay. And that's an issue because, technically speaking, our element stiffness matrix involves the integral of these expression of the shape function derivatives, right? And so when we integrate these, okay, we can no longer just pull it out of the integral like we did with the triangular example. The only reason we were able to do that with the triangular element, was that everything in the matrix was a constant. Right? But if it's not a constant, if it's still a function of x and y, then we still have to integrate it, right? And all of a sudden now we have a big issue because we're performing an integral in 2 dimensions on a triangle, or in this case a rectangle of arbitrary shape and orientation. Okay? Right, and that's an issue because that's just hard. It's not impossible, but think about doing this, hundreds, thousands, millions of times for a given mesh. And that starts to become pretty difficult, especially if you have to kind of reformulate your integral based on the shape. Okay. All right. So we're at a little bit of an impasse, right? So if we were to kind of continue on in the same kind of vein that we did with the triangle, we'd have to, we'd have to become really good at integrating very quickly, right? So we need another approach here. And so the other approach that we're going to use here is something that we've used before. We haven't used it in 2D yet, though, which is Gauss quadrature. So Gauss quadrature is going to come to our rescue, where Gauss quadrature. Remember, the beauty of Gauss quadrature is that you can perform integrals without actually having to perform that antiderivative, which is normally kind of the limiting step for integration, right? And so as long as you have an expression for the integrand, you just plug in certain expressions for the integrand, and then we go from there. Okay. So our next topic here is to do Gauss quadrature in 2D. But before we kind of jump into the details for that, are there any questions on this? Okay, good. All right. So let's look and see what Gauss quadrature looks like in 2D. The good news is that it's not that different. You're basically just going to be applying Gauss quadrature in the x direction and then Gauss quadrature in the y direction. And so you're just kind of doing the same thing twice. Right? But just to kind of refresh your memory, Gauss quadrature, the reason we like doing this is that it allows us to perform integrals, by just performing a weighted sum instead of doing kind of the antiderivative. And so basically we're taking an integral here. If you remember correctly, Gauss quadrature only works when our integration bounds are -1 to 1 of f of x at y dx dy. Okay. So Gauss quadrature says that we can approximate this. And so sometimes we end up with the exact result, but a lot of times we end up with an approximation of summation of some weight. And I'll try to make this a little bit distinct from our weighting function. This is not the same as our weighting function. This is the weight of our weighted sum. Okay. So that's sharp W multiplied by our integrand here, evaluated at certain points. Okay. Where I is equal to 1 up to the number of Gauss points. So this expression right here is the integrand right? So that expression there is the integrand evaluated at the Gauss points multiplied by a weight. Okay. All right, and so the question is, for any Gauss quadrature problem is to one, determine, what the locations of the Gauss points are. Okay. And two, at each Gauss point location, what are the associated weights? Okay. So once you determine those two things, then you can perform that integration. Okay. Okay. So I'm going to go over two rules with you, or two Gauss rules in 2D. These are just the most feasible ones, just kind of based on kind of what we have. So one popular one is to simply use a single point. So this is a 1-point rule. Okay, so this is our 1-point rule in 2D. Okay. So the 1-point Gauss rule in 2D is pretty straightforward. So we're just going to evaluate our integrand at the centroid, or at the centroid at 0, 0. we're gonna evaluate the integrand at 0, 0, and the weight is 4. So in other words, integral from -1 to 1, integral from -1 to 1 of f of x comma y dx dy is equal to 4 times f of 0, 0. Okay. So this is the simplest one you can do. You're just evaluating the integrand at the centroid, or at the origin, I should say, and you're just multiplying by 4. Okay. All right, and so this of course is the simplest, but of course it's not the most accurate. This will help. This will work if you have a very simple integrand. So let's say you have an integrand of just strictly linear functions, then this is going to be perfectly fine. But the next one, probably the most common one that we use in finite elements, is the 4-point Gauss rule in Fullerton. And so the 4-point Gauss rule is really just kind of a generalization of the 2-point rule that we used in 1. Okay, so for 4 points, we're gonna have 4 Gauss points here. So I'm actually let me make it into a table. Okay. Give xi, yi for Gauss point 1, Gauss point 2, 3, and 4. Okay. So the first Gauss point is going to be at -1 over √3, and the y point is -1 over √3. The second Gauss point is going to be +1 over √3, -1 over √3. And we have +1 over √3, +1 over √3, and then -1 over √3, 1 over √3. Okay. And our weights, wi's, are just going to be 1 all across. Okay. And so our integral here, so double integral from -1 to 1, integral from -1 to 1 of f of x comma y dx dy is equal to, we're going to evaluate that integrand at each of these Gauss points and just simply add them all up together. Okay. So we have f of -1 over √3, comma -1 over √3, plus f of +1 over √3, -1 over √3, plus f of 1 over √3, 1 over √3, plus f -1 over √3, 1. All right, so pretty straightforward, right? And so, we've already done kind of 1D Gauss quadrature, so this is just kind of doing the same thing, for that. Any questions on this before we do an example? Okay, all right, so let's do an example really quickly. This will be the last thing we do today. Okay, so let's use Gauss quadrature to evaluate the following integrals. We're gonna have integral from -1 to 1, integral from -1 to 1. Okay. So our integration bounds are good, so we know that we can apply Gauss quadrature to this. And our integrand is x squared y plus 3 dx dy. Okay. Okay. Actually, first let's evaluate this integral exactly. So let's see, this is just a test, right? So let's see if our Gauss quadrature gets the same thing. Okay. All right. So if we're going to evaluate this exactly, we're going to make use of basically I think it's called Fubini's rule in multivariable calc. But basically, we're just going to integrate one variable at a time. Okay. So let's do the x integral first. Okay, so let's do this. So if we integrate on x first, we get integral from -1 to 1 of quantity x cubed over 3 times y plus 3x, evaluated from x is equal to -1, or x is equal to -1 to x is equal to +1 dy. Okay. All right. And so if we evaluate at this at those integration bounds, we get +1 cubed divided by 3 multiplied by y plus 3 times 1 minus the -1 cubed times y divided by 3 minus 3 times -1. Okay. dy. Okay. And so we simplify this, we get integral from -1 to 1 of a 2y over 3 plus 6 dy. Let's integrate this expression in terms of y. Right, so we do that, we get a y squared over 3 plus 6y. Okay. Evaluated from y is equal to -1 to y is equal to 1. Okay. We plug in the integration bounds for this, we have a 1 squared over 3 plus 6 times 1 minus, we have a -1 squared over 3 minus 6 times -1. We simplify that out and we get 12. All right, so that's what we're shooting for. So our Gauss quadrature, if all things go well, you know, we have basically a second order polynomial here. Then we should get 12, or at least maybe something close to 12. Okay. Okay, so now let's evaluate this using Gauss quadrature. So let me write out the original integral again. So we have a double integral from -1 to 1, -1 to 1, x squared y plus 3 dx dy. Okay. So we're going to take our integrand here. So our integrand here is x squared y plus 3, and we're going to evaluate it at each. We're going to evaluate that at each of the Gauss points for them, and we're gonna just add them up together. Okay, so let's go ahead and start. So our first Gauss point is -1/√3 for x and -1/√3 for y, and so that's going to be -1/√3 squared times -1/√3 plus 3 plus, okay. Then we have the second Gauss point. So the second Gauss point is a +1/√3 for x and a -1/√3 for y. And so that is 1/√3 squared times -1/√3 plus 3. Okay. Plus third Gauss point here is a +1/√3 for both x and y. Okay. So you have +1/√3 squared multiplied by +1/√3 plus 3. Okay. And then we have the final Gauss point. So the final Gauss point is x is equal to minus 1 over root 3 and y is equal to positive 1 over root 3. Okay. So we have a minus 1 over root 3 squared times 1 over root 3 plus 3. Okay. All right, and so all we have to do here is just add this all up together. Okay. It looks a little bit scary, but you're going to see a lot of these terms kind of cancel out. Because if you look at a lot of the common terms here, right? So if we look at the overall sign of the root 3 terms, right? We look at this term right here. This is basically a 1 over root 3 cubed. And we have a minus sign. So this has a minus sign in front. Okay. And make that into just a minus sign. I don't know why I did minus 1. Okay, we look at the next term here. We have a positive 1 over root 3 times minus 1 over root 3. So this is again 1 over root 3 squared. But the ending sign for this is going to be negative. Okay. We have the same expression here. So we have a 1 over root 3 squared times 1 over root 3. So all those terms are positive. So this is going to be positive. Okay. And then we have this thing here, which is a positive 1 over root 3 multiplied by negative 1 over root 3 squared. And so the ending sign for this is going to be positive as well. Okay. So we have two negative terms with the same value and two positive terms with the same value. So all these are just going to cancel out when we add them up together. And so all we're left with in the end is 3 plus 3 plus 3 plus 3. And so we have 3 times 4. And 3 times 4 is 12. And so if we compare that to our exact integral, we see that we get the exact same thing, right? So, so that's how you apply Gauss quadrature in 2D, right? It's a little bit more work than 1D just because you have more terms to evaluate, or more Gauss points to evaluate, but you know, the principle is the same, right? Instead of performing the antiderivative on the integral, we just evaluated at the different Gauss points. Okay. All right, any questions on this? All right, question. So how accurate can we expect Gauss quadrature to be in 2D? So it's the same accuracy as in 1D. So if as basically the number of Gauss points kind of determines, you know, the power of the polynomial that you can go up to. And so even though it's a 4-point Gauss rule, I consider it to be kind of 2 points in X direction, 2 points in Y direction. And so you can evaluate up to a quadratic function in those dimensions, right? And so here we have a X squared. So we can do it exactly with 2 points. And then we have a linear function in Y. That means using 2 points, we're going to integrate that exactly as well. So as long as the order kind of matches the number of Gauss points in that direction. Mm-hmm. Right. Any other questions on this example here? All right. So before I leave you guys today, we're going to end a little bit early today. So this looks great, right? And so Gauss quadrature in 2D, you know, looks like it's just an extension of 1D. We just have one problem. It's a very big problem, but it is just one problem, right? This only works if our integration bounds are -1 to 1, right? If you have an arbitrary element, so let's say you have an arbitrary rectangular element, you know, odds are, you know, you're not going to be integrating to -1 to 1. So this is the exact same problem that we ran into in the 1D case, right? In the 1D case, we developed this Gauss quadrature. We thought it looked great, but then we saw that its application was very narrow because most of the times we're not integrating from -1 to 1, right? If you remember, the way that we solved this in one dimension was that we performed a change of variable. And so instead of integrating over the original variable, we changed the variable. So we adjusted our integrand so that we can, integrate from -1 to 1. So we're going to do the same thing here. We're going to perform a change of variable. So that's going to alleviate our issue. So that change of variable will let us basically integrate, perform an integral on any expression, on any bounds. Okay. The problem is that when you do a change of variable in 2 dimensions, especially when you involve things like gradients and things like that, it becomes a lot more complicated. Okay. And so the change of variables in 2D, this is going to lead us to kind of the ultimate kind of discussion that we're going to have in this class, which is isoperimetric elements. So in some sense, we've kind of been building up to this topic, for this entire class. And so, this is kind of the final thing, and you'll see it all kind of come together after the midterm. All right, any final questions on this? Okay, all right, so that's all we got time for today. So next time I see you guys on Thursday, we'll be taking the midterm. If you have any final questions before the midterm, don't be afraid to email me. I'm always happy to answer some emails. Especially if you notice, if you have some questions on homework solutions that I post, I think a couple people caught a couple typos. So definitely make sure you let me know if anything confuses you. Okay. All right. So thank you guys for coming today. I hope you guys have a good rest of your evening, and I will see you on Thursday. Yeah.
So we get the exact solution if the height of the polynomial is equal to or less than the number of Gauss points.
Yes. Gauss in that direction.
But what about
Yeah,
trig
how long have I
functions
been
like
seeing
sine,
this?
cosine?
Yeah, so those ones there's no rules for exactness for Gauss quadrature. For Gauss quadrature works over the polynomials.
Okay.
You'll get something that's decently close, like it's okay, but it's never going to be truly exact like it is for polynomials. So if you have a trig function, honestly for finite element trig functions are pretty unusual. So if you have trig functions,
That 450 something, 454?
Probably something like
I'm on.
the name is escaping, but there's another numerical integration technique that's better.
That's so stupid.
And the other question.
I guess I'm waiting to get.
Why do we have different names for the boundary conditions? If it's what we do.
No, halfway,
Like
45.
we, instead of having Newman and Dirichlet, we've got
Oh, no.
natural
no, I-
and essential boundary conditions.
Yeah, essential, it depends,
Yeah,
depends on the textbook, honestly, that you read. Essential boundary conditions are the same thing as Dirichlet, so those two are essentially the same.
I don't see it.
They're called essential boundary conditions
Yeah,
because you need at least one Dirichlet boundary condition to solve a problem itself. And then natural boundary conditions are called Neumann, just because of. You kind of get into the history of the development, but basically, the reason they're called natural boundary conditions that a lot of times
But it was
people
Megatron.
don't have a boundary condition. You just said it to be.
Yeah, I'm not seeing it.
Okay.
Maybe I just
So like
imagined it.
natural one.
Maybe.
So I think in the notes, I use that terminology.
Maybe
Essential
it's
and natural, but-
Maybe,
but
I feel like
same thing
that's
as
probably.
Dirichlet.
Yeah, the notes is kind of going.
I guess
back and
it's for-
forth.
Yeah, I know.
And it's-
about refrigeration?
I'm having to
Okay.
add
I don't know.
or swap out the words.
Yeah, I know, I was a little bit sloppy making the note. Essential boundary condition is the same thing as Dirichlet, and then natural boundary condition is the same thing as.
Not really good.
Okay.
Yep.
We might throw.
Right. Sorry, Brianna. Let me see. My key source and interior node, how we. Yeah, let's talk about this offline.
Yeah, I think
That's a longer answer. So guys.
Gotta try to wait.
So I know it's evaluated wherever X is the known condition, but
Yeah.
can we solve it? Do we always just default to the W times T times A, or do
Yep.
we put things in?
So you evaluate those at the boundary, so, so a lot of times the, like say like the area function.
Yeah.
So the area is gonna depend, it's gonna be a function of X.
Yeah.
right? And so you're gonna evaluate that, when you plug in for X for that one, it's gonna be at the normal boundary. So if the normal boundary is at, let's say, at the very end of the domain, you're gonna plug in X as that, of my person. Or if the normal boundary conditions at X equals 0, you plug in X is equal to 0.
And the known condition be anywhere along the length?
So for a 1D problem, it's either gonna be at the beginning or,
Okay.
it's, yeah, kind of impossible to have it.
Yes.
For 2D, it can be almost anything. So that's what kind of complicates things, but for
Yeah.
1D, it's either gonna be at the beginning or at the end.
Okay. I think, thank you.
Yep, yep. Um. Let's see, well, actually, most people have left right now. When applying these tools to interior node. So for an interior node, basically you're gonna be evaluating, if you're doing finite, so this is finite difference, I'm guessing, right? With the nodal values. Basically, when you incorporate into the equation, you just evaluate the thermal generation term or the heat source term at the location of the node, right? So for each node, you know what the coordinates are for the node. And so you plug in just the X and Y coordinates of that node, or Z if you're in 3D as well. And so in MATLAB, you would plug that into in your for loop, you're keeping track of the nodes for each of the coordinates for each of the nodes, and you'd plug it into that function there. Now you may have to multiply depending on your exact formulation. Let's say that you multiplied it by, let's say if you're doing an unsteady problem, you probably multiplied it by delta T. You probably multiply by delta X squared, something like that. And so you have to account for those terms as well. So when you insert it into the right-hand side vector, you may have to multiply it by either delta T or delta X or delta X squared, just to kind of keep it consistent with the rest of the equation. Oh, finite volume. Okay. So for finite volume, we also have to integrate it. And so I think I don't remember exactly. It's been a while since I taught 417. But in 417, I think we also use like some form of Gauss quadrature to evaluate our integral, or some kind of numerical integration technique. I think we just simply use the midpoint rule. And so you would basically evaluate the heat source term at the middle of the cell of your finite volume cell. And then again, you would multiply it by just any kind of grid spacing or time step size, just to keep it consistent with the rest of the equation. Yeah. Does that kind of make sense? I think do you still have our notes from 417? It might be easier to kind of look at that. Okay. Are you doing something for work with that, or? Okay. Yeah. Yeah, I would go back and look at the notes. I can send you kind of the excerpts of the notes, kind of exactly where it is once I get back to my office, if that helps. Okay, yeah, so I'll head back to my office. I need to take care of a couple of things first, but I'll send it to you before I head home from today. All right. See you guys on Thursday.